We're going to go ahead and jump into Chapter 1 and get started on some definitions and terms and get a little bit of background here. And then the next couple of videos we'll move into significant figures and scientific notation. So first off, what is chemistry? Well, we can think of chemistry as being the study of the composition, structure, and properties of matter, and also that includes looking at the energy that's consumed or given off when matter undergoes a change. So there's kind of two parts to this idea. A lot of what we'll look at has to do with the composition, structure, and properties of matter, but then there's a specific area called thermodynamics where we look at the energy that's consumed or given off when matter undergoes some type of change. And that can be a change in state. So we can think about going from, say, a liquid to a gas, or a gas to a liquid, or a solid to a liquid, or this can be undergoing a chemical reaction. So to define a few things here, matter is anything that occupies space and has mass. So everything that you see around you is matter. The chair that you might be sitting in is matter. Tables are matter. The floor, everything around you, the air that's around you is matter. Mass defines the quantity of matter in an object, and typically we measure mass in grams or sometimes in kilograms because many objects are too small to be measured just in grams. A gram is actually about the weight of a paperclip, so oftentimes we use kilograms. And energy is defined as the capacity to do work. So, of course, the study of chemistry would not be complete without talking about the periodic table. In fact, a lot of what we do revolves around the periodic table. So what you see on the periodic table is a large number of elements. So elements are fundamental substances that cannot be broken down any further. So they're a fundamental unit of looking at matter. The way that we abbreviate elements, because we don't want to write them out all the time, is we typically use a 1 or 2 letter abbreviation. So most elements, their abbreviation makes sense. For example, O is oxygen, Si is silicon, H is hydrogen, He is helium, N is nitrogen, and so forth. But there are some elements that their abbreviation doesn't really seem to make sense. For example, Pb is the abbreviation for lead. The reason for that is that those names, or those abbreviations, come from their Latin or Greek names. So, for example, the abbreviation for lead comes from its Latin name, plumbum. A couple of others, or a few others that you will notice, Hg is mercury, Fe is iron, a couple more that we use quite frequently, Na is sodium, K is potassium, and you will get introduced to quite a few others as we move on throughout the semester. The smallest unit of an element is known as an atom, so we will talk a lot about atoms as we move through the semester. Molecules are made up of 2 or more atoms. So a few examples that we have listed here are H2O, N2, which is nitrogen gas, H2, which is hydrogen gas, ammonia. We also have a picture down here of carbon dioxide. And we could go on and on all day with examples of molecules. But to be a molecule, we need 2 or more atoms. A compound is a combination of 2 or more elements. So the key difference between the definition of a molecule and a compound is that a molecule just needs 2 or more atoms. To be a compound, it needs 2 or more elements. So things like H2O or ammonia, which is NH3, or C9H8O4, which is the molecular formula for aspirin, would be compounds, and they would also be molecules. Things like N2 or H2 would be molecules, let's get a little more space here. Let's see. Those would be molecules, but not compounds. Because they have more than one atom, they have 2 or more atoms in them, but they do not have 2 or more elements. So something can be a molecule, but not a compound. A molecule is the smallest unit of a compound, and compounds themselves can be broken down into their individual elements by chemical means, meaning we can do some type of reaction. So for example, water, I can't pour your water on the table and hit it hard enough with something to break it apart into hydrogen and oxygen. We can't do that by physical means, but by chemical means we could pass an electric current through it under the right conditions and get hydrogen gas and oxygen gas out of our water. So when we have a particular compound, we have the law of constant composition. All samples of a particular compound have the same elements combined in the same proportions. So for example, something like water will always have 2 hydrogens for every 1 oxygen. Or if we take something like ammonia, it will always have 1 nitrogen for every 3 hydrogens. So you will never find in a molecule of water that has a different number of hydrogens or a different number of oxygens. It will always be in a ratio of 2 to 1. So when we talk about compounds and molecules, we have to talk about how those different atoms are held together. So there are 2 different bonds that we will talk about right now. One is covalent bonds, and in covalent bonds, the electrons are shared between the atoms. In an ionic bond, elements are transferred between atoms. So we end up with one element that has a positive charge and one element that has a negative charge. There are different ways that we can represent compounds that have covalent bonds. So one way that we can represent something that has a covalent bond is a structural formula. So we can show how all of the atoms are connected together. We can give those compounds names, and we do give those compounds names, and we will actually talk about in Chapter 2 how we name different compounds. We can write a chemical formula, but the problem with a chemical formula is that it gives you the number of each type of element, but it does not show you how those elements are connected. So if we looked at C2H6O, We don't know just from looking at that how we would connect those. A structural formula shows us how those elements are connected. And then we also have here a ball and stick model where we can see more in 3D how those carbons, hydrogens, and oxygens are connected to each other. In an ionic bond, one of the compounds gives up its electrons and becomes a positively charged ion. The other one gains electrons. It takes the electrons and becomes a negatively charged ion. So the names for these, cations are the ions that lose an electron. So if they lose electrons, they have a positive charge. Anions are the ones that gain an electron, so they become negative. So if you like little mnemonics and word associations to help you remember things, you can think about anions has this extra N here. It's a negatively charged particle. So anions gain an electron and are negatively charged. We can further classify matter as pure substances or mixtures. So pure substance is something like an element or a compound that has the same physical and chemical properties throughout. In a pure substance, we can't separate into a simpler substance by a physical process. We can do it by a chemical process sometimes, but not by a physical process. A mixture is a combination of two or more pure substances, and mixtures can be separated by physical processes. We can further classify mixtures as either homogeneous or heterogeneous. So in a homogeneous mixture, the components are distributed uniformly. So for example, if we take something like vinegar, vinegar is actually apple cider dissolved in water or mixed with water. So if you look at a bottle of vinegar, it looks the same throughout. You don't see a layer of the vinegar and a layer of water. Or actually vinegar is acetic acid in water. So you don't see a layer of acetic acid and a layer of water, you just see vinegar. Or another example would be seawater, unless you get a sample of seawater that has some seaweed or dirt. And then if you just get the water by itself, it will look the same throughout. But it's actually a mixture of different salts and things that are dissolved in water. A heterogeneous mixture is something that's not distributed uniformly. So you may actually have distinct regions in your heterogeneous mixture. So one example would be something like sand and rocks. So that example is a little bit more obvious. You can see the rocks and you can see the sand, and you could go through and pick the rocks out. Or this bottle of vinegar that we have, we can see the different layers. We can see the oil layer here at the top, and we can see the layer that has some other little components in it. Or another example would be something like oil and water. So if you look at a mixture of oil and water, yeah, you might shake it up and it might look mixed for a few seconds, but if you let it sit, you're going to see a layer of oil and a layer of water. So those are heterogeneous mixtures. So we can kind of break matter down into distinct categories. So if it can't be separated by a physical process, we know that that's a pure substance. Pure substances can further be divided into elements if they can't be broken down by a chemical reaction, or compounds if they can be broken down by a chemical reaction. If we have something that can be separated by a physical process, we have a mixture. If a mixture looks uniform throughout, then that's a homogeneous mixture. If it does not look uniform throughout, that's a heterogeneous mixture. So here's a few examples for you to practice with and determine if these are elements, compounds, or mixtures. And then we'll actually talk more about these in class. So let's talk about some of the properties of matter. So we can divide properties of matter into intensive properties and extensive properties. Intensive properties are things that are independent of how much substance we have. So for example, the color of a substance doesn't depend on how much you actually have. It's going to be the same color whether you have a gram or a kilogram or 1,000 kilograms. The melting point is going to be the same. The boiling point is going to be the same. All of those things about how it looks are going to be the same no matter how much you have. An extensive property is something that varies with the quantity of substance that you have. So for example, the volume. A kilogram is obviously going to take up a larger volume than a gram. The mass is going to be different depending on how much you have. Another way that we can divide properties of matter is by physical properties and chemical properties. So physical property is a property that can be observed without changing the substance you have into something else. So for example, if we want to observe the color or the luster, which is how shiny something is, we can do that without having to change our substance into something else. We can just look at something and see what the color is or how shiny it is. You can feel it and determine how hard it is. You can measure the melting point and boiling point, and you would have to change states. Melting would be solid to liquid, boiling would be liquid to gas, so you would be changing states, but you would not actually be changing the substance into something else. You can measure the density, you can weigh the substance and measure how much volume it takes up, but you're not going to change it into something else by doing that. A chemical property is a property that can only be observed if you react with the substance with something and form another substance. So for example, if we look at the flammability of something, the only way to determine how flammable something is to burn it, and then you're going to form an oxide of that compound. Another example would be something like oxidation. To determine how easily we can oxidize something, we would have to react it with oxygen, which means that we're going to get an oxide of that compound. So if you have to react your substance with and form something else, it's a chemical property. So we can also talk about the states of matter. So there's 3 states of matter that we'll talk about. There's actually a 4th, which is a plasma, which is kind of like a gas but at a much higher temperature and has slightly different properties. But we don't really deal with plasma a whole lot, so we won't talk about that in this class. Solids are the state of matter that have a definite shape and a definite volume. Liquids have a definite volume, but not a definite shape. So for example, if you take your water and pour it from the bottle you have it in into a cup, it's going to take the shape of the cup. But you don't change the volume of liquid, you still have the same number of milliliters you had to start with. Gases have neither a definite volume nor a definite shape. So if I take a gas that's in a 5-liter container and I transfer it to a 10-liter container, it's going to expand to fill that 10-liter container. So we can also change states of matter. So the first few of these you're probably pretty familiar with. Melting is going from a solid to a liquid. Freezing is going from a liquid to a solid. Vaporization is a liquid to a gas, and condensation is a gas to a liquid. Now be very careful with vaporization. Don't confuse vaporization with evaporation. Evaporation is something that only occurs if it's spontaneous. So, for example, if I leave a cup of water sitting on a table, eventually some of it's going to evaporate if I leave it there for a few hours or a few days. That occurs spontaneously at room temperature. It might not be much of it that evaporates unless I leave it there for a really long time, but that process is spontaneous. Vaporization is any time we're going from a liquid to a gas. So I can force vaporization to happen. I can add heat. I could put my water in a pot and put it on the stove and add heat to it, and it would boil and turn from a liquid to a gas. So that would be vaporization, but not evaporation. So the more general term is vaporization. The two that might be a little less familiar are sublimation and deposition. So sublimation is a solid to a gas. So if you think of something like carbon dioxide in a solid is what is known as dry ice. If you leave dry ice out at room temperature, it does not melt into a liquid. It turns directly from a solid into a gas. So that process is called sublimation. If we go in the opposite direction, if we go directly from a gas to a solid, we call that deposition. So we'll leave significant figures for the next video and we'll stop here. And then we'll pick up and talk about significant figures and scientific notation and get into some conversions later on.